You ever just stop and think about the thing you're watching this on right now? Your phone, your computer. It's this incredible piece of tech. But how does it work? I mean, how do we get our thoughts into its brain? Well, that's what we're going to do today. We are unlocking the brain of your devices.
And I'm not really exaggerating here. I mean, at its heart, every single computer is made of silicon. That's basically just sand, right? Purified sand. And what do? We zap it with electricity. So that brings us to the big, kind of mind-blowing question. How does a rock that we tricked with lightning actually think?
Okay, so the answer, it actually starts with something that is so simple. You look at all this amazing complexity around us, right? Your smartwatch, a giant supercomputer, and at the end of the day, every single one of them only understands two things. Just two, on and off. That's it. We just call them 1 and 0. That is the entire vocabulary these things have. All right, so if the computer only knows two words, how in the world do we have a conversation with it, right? We need a language, a kind of secret language, built entirely on just on and off. And that language, it's all governed by a set of rules. It's called Boolean Algebra. Now, hang on, don't let the word algebra freak you out. Seriously, it's not about complex math. It's way simpler. Think of it more like the grammar. It's the grammar for this language that only has two values, true or false, on or off, 1 or 0. See? Not so bad. So these rules you're seeing here, this is the absolute foundation of all digital logic. It really is just like grammar. You know how in English, dog bites man means something totally different from man bites dog? Well, these rules do the exact same thing for the computer. They let us build these complex logical statements that the machine can understand perfectly, with zero confusion. Okay, great, so we've got the grammar down, but, a language is pretty useless if there's no one there to speak it or to act on it. So let's go meet the microscopic little workers who actually put all these rules into action. And these little workers are called logic gates. So what is a logic gate? It's just a tiny physical device, basically an electronic switch. And its job is simple. It takes in some 1s and 0s, and then it spits out a new 1 or 0 based on one of those simple Boolean rules we just talked about. They're like microscopic decision makers, each one with one very specific job. All right, let's meet our first one. This is the NOT gate. It is the simplest of all of them. You can think of it as the rebel of the group. The contrarian. It does just one thing. It flips whatever you give it. You hand it a 1, it spits back a 0. You give it a 0, it gives you a 1. That's it. Simple as that. And this is so cool because it shows you exactly how engineers think about these things. You've got the Boolean expression. That's the mathy way to say it. Then you've got the logic symbol, that's like the blueprint drawing, and finally the truth table, which is just the plain, simple proof of what it does. Input, output, done. It's 3 different ways of telling the exact same simple story. Okay, next up, the AND gate. Now this guy is a lot stricter. I like to think of him as the bouncer at a super exclusive club. He's only going to let a 1 out the other side if, and only if, all of the inputs are also a 1. If even a single 0 shows up, nope, the output is 0, no exceptions. Tough guy. And you can see this perfectly in its truth table. Look here, 0 and 0, nope, that's a 0. 0 and 1, still 0. 1 and 0, you guessed it, still 0. It's only in that very last row, when both A and B are 1, that we finally get a 1 out. It just perfectly captures that strict all-or-nothing personality, doesn't it? But then, on the complete other end of the spectrum, we have the OR gate. This is the super chill, easygoing friend of the group. The OR gate is way more relaxed. It'll give you a 1 output if any of its inputs are a 1. As long as it sees at least one on signal coming in, it's like, yeah, sure, come on through, and sends an on signal out. And again, the truth table lays it all out for us. I mean, look at it. The only way you're ever going to get a 0 out of an OR gate is if everything you put in is 0. Any other combination, you're getting a 1. It's the total opposite philosophy of that strict AND gate. So there you have it. We've got our basic building blocks now, our NOT, AND, and OR gates. By themselves, they're pretty simple. But what happens when we start sticking them together? This is where the real magic begins. It's like we've got a box of logic bricks, and now we can start building some really cool stuff. When we start linking these logic gates together, we create what's called a circuit. And a circuit is really just a team of these little decision makers all working together in a chain. The output of one gate just becomes the input for the next one down the line. And that's it. That's how we go from these super simple rules to incredibly complex behaviors. Okay, so what can we actually build with this stuff? Let's try something that sounds kind of impossible, right? Something you wouldn't think you could do with just a bunch of on and off switches. Let's try to build a circuit that can do math. Yep, let's build something that can add. And this right here is the blueprint. This is for something called a half adder. And just look at it. It's so elegant, so simple. It's just two of our logic gates. One is an XOR gate, which is just a fancy type of OR gate, and the other is our old friend the AND gate. And they're just wired together in this specific way. That's the entire design. But what does it actually do? Well, this truth table, it tells the whole story. Just focus on that very last row. When input A is 1 and input B is 1, what happens? The sum output is 0 and the carry output is 1. Wait a second. 1, 0. In binary, that's the number 2. Oh my gosh, we just taught a rock how to add 1 plus 1. That's insane. Okay, so now that we can add, we can start chaining these circuits together to do all sorts of incredible things. But as we start to build bigger and bigger things, we hit a new wall, a new problem. And that problem is complexity, which brings us to the really important art of simplification. I mean, just think about it. The processor in your phone or computer has billions of these tiny gates crammed inside. So if our designs are messy or inefficient, they get slow, they get bulky, and they get super power hungry. Your battery would die in 5 minutes. So for technology to keep getting better, we have to make our logic as clean and efficient as possible. And this is where that Boolean algebra stuff comes right back around. So on the left, you've got this complicated, tangled mess of a circuit. But by using those grammar rules we talked about at the beginning, an engineer can simplify that whole thing down to the clean, elegant design on the right. Get this, they both do the exact same job, but one is just so much better. Faster, smaller, less power, it's a huge deal. Okay, let's pull back for a second. Let's zoom all the way out. We started this whole journey with a simple on/off switch. That's it. Then we gave it a rule book, we introduced it to some tiny decision makers, and we showed it how to build things by working together. And from that one simple switch, we get everything. So seriously, the next time you tap your phone screen or you swipe or you play a game, just take a second to remember what's actually going on under the hood. Every single one of those actions, it's just being broken down into millions, sometimes billions, of tiny, tiny yes or no questions. And they're all being answered by those little logic gates in an absolute instant. It's a pretty wild thought, isn't it? Using just two ideas, on and off, we've built this entire digital world. We literally taught rocks how to think, using a vocabulary of just 2 words. And that leaves us with one final, really exciting question, doesn't it? What are we going to ask them to figure out next?